transmission lines and standing wave ratio are a couple of the most misunderstood things out there in communications. Many old wives' tales that are just plain incorrect, and I found incorrect information on the internet as well. You've got to be careful about what you see on the internet, because oftentimes someone will put something up and then people will parrot it, and then the same wrong thing gets passed from one to the other. And transmission lines in some sense are even more complicated than antennas. And I can tell you that as a physicist, the course in a physicist training that makes or breaks you is a book written by a man named Mr. Jackson, and it's called Electromagnetic Theory. And it is a deep dive into electrodynamics. And if you're going to be a physicist, you'll make it through that class. And if you're not going to be a physicist, you don't make it through that class. So that's how it works. So transmission lines, everybody's got a transmission line. I'm going to be switching between sitting here at the computer, and then I have another camera pointed at the board, so I'll work at the board there. But a transmission line is something to get your signal from one place to the other. That's what it's for. It'd be nice if you could have your transmitter hooked up right to your antenna. In fact, some of you do. If you've got an end-fed wire, which is one of the most popular antennas out there, I used that for many years, you essentially have no transmission line whatsoever. But when you have an end-fed wire, you get what we call RF in the shack, and it can cause all kinds of problems. It wasn't a problem with tube gear, but with solid-state gear, RF in the shack can just be the difference between having something work and having something not work at all. So there's usually a separation between the source of the RF and where it's going to be connected to the antenna. And to do that, we use a transmission line. And there are quite a few different types, but the ones that we as hams encounter, there are primarily two types. There's the transmission line where it is simply two conductors that are next to each other, parallel to each other. And I'm going to show you, by the way, how you can make some of your own open wire transmission line. You don't have to buy it. There's two wires, like number 14 wire, about 3 or 4 inches apart. There's ladder line. There's television line, which is much rarer nowadays. And there's a specific type of twin lead for transmission work. But these are all essentially just two conductors that are parallel to each other. The other kind of line that we find in common use is coaxial cable. And coaxial cable, coax means axial, common axis is what it means. So that what you've got is a wire inside of a cylindrical conductor. And in some cases, these really on the left side here, they are all the same thing. It's just pretty much how they handle the shield that is different. There are some lines used in commercial work. There's a type called heliax. Some of you might be VHF, UHF people out there. Heliax uses discs rather than the plastic all the way through. It has much lower loss, and it can be, some of these lines are filled with nitrogen. But for you and me, average a ham, we're going to have a transmission line, a coax, with some sort of a solid dielectric here in between the outer cylindrical conductor and then the wire in the middle. And there are many different types of coax. Comes in many different sizes and so on. If you go to an ARRL handbook or an ARRL antenna book, you can get a list of line specifications. This is just one. It might be too small for some of you to see, but in the first column is the name. The second column is what we call the impedance, and I'm going to talk about that quite a bit. And you can see how many different types of coaxial cable there are. And then further down, there's open wire line, and then there's what we call window line, which is a very popular line used in ham radio today. If you buy a G5 RV antenna, it's probably got some window line, plastic parallel window line on there. If I zoom in on this thing, let me see if I can zoom in on this a little bit. What we find, what we find is, if I can just, get a little bit better. Let me zoom in even more. What you see here in the first column is, let me pick up a pointer, is the name of the line over here. Here's RG8, RG8X, RG11, there's RG213, and on it goes. But these are all the various specifications that you find. And the physical specifications, one of the things you'll notice is that if you look at the outside diameter here in this fifth column, you'll see a lot of these are like 0.405, 405, 405, 420, 405, 405. And that's because the connectors, the SO239 connectors on the end of the line take a specific size. So that's kind of important if you have the connectors, all right? And then further down, you'll see, you also see in the first and second columns, I'm going to talk at great length about this, the impedance of the line, and what that actually means. I think I made that, there we go. 75 ohms, 52 ohms, 75, 93. If you go down to the open wire lines, it's 600. I'm going to talk at great length here in a moment about what that actually means. Also, in the third column, there's something called the velocity factor. And this is percent. This is the percentage of light speed that a radio wave travels down the line. Light travels at 670 million miles an hour in free space. It does not travel at that speed in transparent materials, and it doesn't travel at that speed in a transmission line either. Most of the time, for most of you, it makes no difference whatsoever. But if you are the type of person that makes phased arrays, if you're combining antennas in the UHF and VHF, combining beams to get more gain for moon bounce work or something, then this velocity factor becomes very important. This is the percentage. You can notice here in RG8, the velocity factor is 75. That means it travels 75% the speed of light in that particular coax. In some other coaxes, RG8 foam, 80% the speed of light. And here you see 66, 86. You see a variety here for these other ones. You see 70%. What it really comes down to is, if this is an important factor to you, is you may want to measure it for a specific piece of coax that you have. It is possible using an antenna analyzer to measure these numbers. But let me talk first, though, about what this characteristic impedance means. So one of the most important characteristics of a line is called the characteristic impedance. It is very important. Very important. Really, it's the most important specification of a transmission line. Typically, for coax, it's typically around 50 ohms. And if you wonder why so many of these things are 50 ohms, it's because after World War II or during World War II, when they started to make coax, they had to standardize it because this is such an important thing and affects the performance of a communication system that they had to ensure that the coax that was distributed had the same characteristic impedance. Otherwise, it would cause a lot of problems. So they standardized it at 50. It's a nice round number. You'll see a lot of them are 52, 51, 50. That's all 50. as far as I am concerned. Open wire line, like I use in my ZEP system, might be 600 ohms. It's much higher. It's much higher than for coax. The value doesn't really have any effect on the performance of the system if it's installed properly and matched properly and so forth. But I'll show you why you get this. One of the things that is so confusing to people is if you take a piece of coax, let me get some here. Okay, here's a piece of RG8U, which is a typical coax you find in your shack. This is a 50 ohm line. This particular one is 50 ohms. But if you take an ohm meter and you hook it up to this, I don't care how you hook the ohm meter up to this, end to end, inside out, no matter what you do, you're never going to get 50 ohms. No way, no how. And so the question comes up, what the heck do they mean by this number right here? What the heck do they mean by that? Well, it's kind of bizarre, but if you imagine taking, say, it's easier if we do it with open wire line. If you take some parallel conductor line and this has to be really long. Make this 93 million miles long. Make this go to the sun. Run a piece of coax or a piece of line to the sun from over here where we've got Mother Earth. So it's 93 million miles of line. Okay? Now, it's just two wires, and we're going to ignore the resistance of the wires. Perfect wire, zero resistance. Okay? Textbook wire. Constant separation between them. Okay? Well, when I look at this, this is about 600 ohms. When I look at this, what I see is a capacitor. Two conductors separated by free space, an insulator. It's a big capacitor. Many, many farads. Many, many, many farads. And if you were to connect a battery to this, so if you were to take a battery and try and connect it to this, you would think that if it were a perfect battery that you get this huge current flow. After all, when you hook a capacitor up to a power supply, it draws this surge of current, and then the voltage across the battery or across the capacitor builds up. So there's a surge of current, and then the voltage across the capacitor will build up, and eventually it will equal the voltage across the battery. Well, if you do that here, that doesn't happen. As a matter of fact, when you hook this up, if you measure the current going into this line, and this is potential V, what actually happens is, if this is an extremely long line, let's call it infinity, a constant current will flow into the line. The current does not surge high and then gradually drop like it does when you charge a capacitor. It's constant. What is preventing it from surging? The answer is that the line itself is an inductor. A straight wire has inductance. We just wind it in a coil to increase the inductance. There's a huge amount of inductance here. So the inductance limits the surge. And the combination of the inductance of the line and the capacitance between the two conductors is such that a constant current will flow. It behaves like a resistor. It looks like a resistor. An infinite piece or an extremely long piece of the transmission line looks like a constant resistance. This is true whether you hook a battery up to it or whether you hook alternating current up to it. I don't care what it is. It behaves just like a resistor, and the value of that resistor is called the characteristic impedance of the line. So if you take some number 14 wire, about 4 inches apart, take an extremely long run of it, and hook up an ohm meter to it, it'll read 600 ohms. Take a piece of coax and run it out, it'll read 50 ohms. The characteristic impedance is what an infinite length of line looks like. In this case, this is 8 minutes, 8 light minutes. So for 8 minutes, it will look like this. Actually, this will look like a 600 ohm resistor for about 16 minutes. And we're going to see what happens here when the signal gets down to the end. That's going to be really, really important to us. That's going to be of great concern, and it will, of course, will involve this, what an infinite length of the transmission line looks like. Okay? It's very important to know what the characteristic impedance of the line is. This is one of the problems you can get into if you go and you buy surplus line. There is a type of line such as this one right here. Let's see, yeah. Looks exactly the same. Looks the same as this. Same diameter. I mean, you wouldn't know that there was anything different between these two. Except this is RG11, and it has a characteristic impedance of 75 ohms. This has a characteristic impedance of 50 ohms. And you might be wondering, well, what is it about the cable that's different? Well, if you get into the physics of it, if you get a book, the antenna book, or the handbook, there are formulas that will tell you, for instance, I think I have one here, that for parallel conductor line, in fact, here's a very nice, let me go to this, okay? This is what a piece of the transmission line looks like. If we break that on the board back there, you can see my image on the board. If you break that down, it looks like a little coil. Looks like a small amount of inductance, and then we hit some capacitance, and then some more of the inductance, and more capacitance, and more inductance, and more capacitance, and you have an infinite number of these strung out in a very long line. That is what the transmission line looks like. An infinite number of little inductors and capacitors wired like this. And depending on the capacitor value and the inductor value, that determines the characteristic impedance. So, for instance, for open wire line, here is a chart that tells you, instead of plugging into some sort of a complicated formula, you can just get this chart out of the antenna book. At the bottom here is the center to center distance, the spacing of the wires in inches. My line at home is spaced at 3.5 inches. And I'm using number 14 wire, so if we come up here to where the number 14 wire intersects the 3.5 inch spacing, you see that the characteristic impedance is about 550 ohms. In many cases, especially with open wire line, it isn't that important to know what the characteristic impedance is. But as I'm going to mention at the end of this talk, one of the uses of a transmission line is as a matching network. You can use a piece of transmission line in place of an antenna tuner. But it has to be a specific length, and it has to have a certain impedance. So in some cases, you might actually construct a piece of open wire line of the proper dimensions to get a particular characteristic impedance. Let me go back to the board here. All right. So, one of the things you'll find that the bigger the capacitance between the lines, which means if you use plastic, okay, here's an open wire line. This is what is typically called, I call this window line. I don't call this ladder line. This is window line. This is two conductors. It is this, but it has plastic in between. And when you add plastic in between, it changes the characteristic impedance. It lowers the characteristic impedance. And further, when you bring the wires closer together, the rules for a capacitor say that when you bring the conductors closer together, the capacitance goes up. So the closer the wires are together and the more dielectric you have between them, the lower the characteristic impedance. So if you cut open these two lines, you will find that the plastic dielectric in between the two of them is different. And that is what changes the characteristic impedance of the line. It is actually possible to go to a manufacturer, and if you need a specific impedance and you say, you know, they can make a special run. They can, you know, be expensive as the dickens, but there's no reason they couldn't use a special dielectric in there to give you a specific impedance. But 50 and 75 for coax is typical. Hundreds of ohms is typical for the open wire line. For the velocity factor is how fast the wave propagates. And the velocity factor is also related to the dielectric constant in between. The velocity factor for open wire line with air is darn close to 1, 100%. It travels at 99% the speed of light. But you put the plastic in between it, and it changes the situation. By the way, I wonder how many of you have noticed this. I used to use this to feed my ZEP antenna, and I replaced it with true open wire line. How many of you have noticed that if you have an antenna tuner on the end of this, that the SWR, the standing wave ratio, changes when it rains? And that is because water is a dielectric, and when you coat these little rectangles with water, water collects on it and changes the characteristic impedance. And that may require you to readjust your antenna tuner when it rains outside. I've noticed a significant change when it really rains. I changed out this and went to regular open wire line, and that solved the problem because the rain just falls through. There are spreaders here, so real open wire line has insulators here to keep it, and they do affect it a little bit. But for the most part, the rain does not affect the characteristic impedance of the line. That's why your SWR changes when one of these lines gets wet. Okay. Now, if I go back here, the question is I'm going to come back to this. One of the key questions that I hope you're asking is, do I care what the velocity factor is, and do I care what Z0 is? What difference does it make? Who cares, okay? What the heck difference does it make? Velocity factor, that's only important if you're using the transmission line as a matching network. Then you have to take this into account. The velocity factor means that the wavelength in the line is shorter. The velocity factor is between 0 and 1. It's a percentage. So for coax, a typical value is 0.66. For open wire, it might be 0.95. What happens is the wavelength in the wire is shorter because it's traveling slower. So the wavelength of a 40-meter signal is not 40 meters. If you want to cut one wavelength of line for the 40-meter band, someone says, I need a wavelength of line for 40 meters of coax, you don't cut it 40 meters long. You multiply 40 meters times 0.66, that's going to be something like 28 meters or something like that, and that's a full wavelength. It's much shorter. But this is what's really important, and that is what I want to concentrate on. To understand why it's important, we have to ask what happens when I send a signal down this line, okay? I send a signal down this line. How do I do it? Well, I'll tell you what. I take my battery. Suppose it's a 9-volt battery. I take a 9-volt battery, and for 1 second, I hook it on here, and then I disconnect it. You know, a transistor battery. I hook it on here, and I disconnect it. Well, this takes light 8 minutes to get to the sun. 8 minutes. It's traveling, this pulse is going to travel almost light speed. What that means is if I'm halfway here, if I connect a voltmeter here, right in the middle, and I have a special voltmeter here which reads 0 in the middle, and I hook it across the line, what's going to happen is 4 minutes later, 4 minutes later, it's going to go up to 9 volts, and then it's going to drop for 1 second, and then it's going to drop back. Okay? So if I hook this up for 1 second, I send a pulse. 1 second. It travels down here near the speed of light. 4 minutes later, out here, this thing will go up to 9 volts, and then it'll go back to 0. And then the question is, then what happens? Well, it's going to travel down, travel down, travel down, and then it's going to hit this open end where the sun is, okay? What happens? Well, one of the ways you can tell what happens is to keep watching this voltmeter here in the middle, okay? And what you discover is that 8 minutes after this bugger goes up to 9 volts and back, son of a gun, it goes up to 9 volts and back again. And then if you keep waiting, if you disconnect this, every 8 minutes it'll go up to 9 volts and down. The square wave pulse, if you draw it, it would be like this. It would be just a pulse, 9 volts high. It would hit here and it bounces off the end. It bounces off the end and come back down, still positive, passes here, we read it, bounces off of this end, and it will bounce back and forth forever. If it's perfect line, doesn't radiate, doesn't have any loss, dielectric loss, perfect textbook line, you've actually stored some energy and it'll bounce back and forth forever. The answer is when it comes down here to the open end, it bounces back. Exactly the same as it came down and will go forever. All right? What if you short the end together? You say, aha, if I short the ends together, that'll short circuit the pulse and it will never come back, right? That's what will happen. So you send the pulse, this thing goes up to 9 volts for 1 second and goes back. And you sit there pleased as punch with yourself. 8 minutes later, son of a gun, it goes 9 volts negative and then comes back. It bounces off. It bounces off. If it's a closed, short-circuited end, it bounces off and its phase is flipped. Its phase is flipped over, okay? And so it comes back here. It bounces. It's not flipped. So we started off, it goes plus, then it bounces, then it goes minus. It hits here, it goes minus, hits here, it gets wet, then it goes plus, and it goes back and forth. Now, I got this little toy. This is why I went into physics, because you can get toys like this. This is a mechanical transmission line, okay? And I've got to bring it out here far enough so that you can see it. I got to get it near the board here. Okay, it's not quite. Let's see. Can you? I think you can see it there, right at the very bottom of your screen. I wish it were higher up, but I'm not going to mess with the camera, okay? I'm going to send a pulse from this end, a big pulse. See it go down and then see it come back? Let me do it again. This is a negative pulse. Whoop. Bounces and it comes back negative, and if it were perfect, it would go back and forth. Well, actually, you're seeing the back better. You're seeing the back here. Okay, let me do it this way. There you go. You can see the positive. See it bounce? You see the bump? It bumps off and it comes back. Now, if I hold this and short circuit it, it gets flipped over. Watch it carefully. It goes negative. It gets bounced and then it goes back and forth. So what happens here is that when a signal hits the end of the line, it is reflected if it's closed, it's reflected if it's open. It's reflected in phase. If it's shorted, it's reflected 100% out of phase. Okay? So the question is, how do you get it to not reflect? The answer is simple. What somewhere in between being totally open and completely shorted is a resistor. And it turns out that if I connect a resistor to this, whose value is equal to the characteristic impedance of the line, when the pulse comes down and sees this resistor, as far as it's concerned, it doesn't know whether it's a 600 ohm resistor or whether it's more transmission line. If this is 600 ohm line, just for convenience, if we put a 600 ohm resistor here, when that pulse gets down here and sees a 600 ohm resistor, for all it knows, it's more transmission line. And so the pulse goes into the resistor and is absorbed and turned into heat. If this were an antenna with that impedance, it would be radiated into space. So if it's terminated here, we get no reflection. This is the special case. This is generally what we prefer to have. We want the energy to enter the transmission line, go down to the load, we call this the load, and we want the energy to be absorbed or radiated by the load, and we don't want any of it coming back. So now I'm going to ask, what happens if some of it does come back? As you can imagine, what if it's not exactly 600 ohms in this case? What if it's bigger than 600 ohms? Well, what's going to happen is some will be reflected in phase. So if the resistance is bigger than, the terminator is bigger than the characteristic impedance, some is reflected, but not all, and it's reflected in phase until you get to completely open, and then it's all reflected. If the termination is less than Z0, then some of it is reflected, but it's reflected out of phase. So now the question comes in, what the heck happens if you have two waves that cross each other like this? What happens if they cross each other like this? That is what can cause problems, okay? That is what can cause problems. Imagine that I have something carrying the wave, and I send one wave going this way, and I have another wave identical to it going that way. They are identical in frequency, same frequency, same amplitude, same strength. You can imagine on my transmission line there, I could take my open wire line and shake it like this a few hundred times. It goes down towards the sun, and then after a while I shake it again, and that one that went down there bounces back, and eventually they cross each other. Now think about it. Think about it. Same amplitude, same frequency. When they encounter each other, the rule for waves is that the resulting displacement, the resulting voltage in this case, is the sum of the two voltages, taking into account a possible negative sign. So if one wave wants to raise it 5 volts, the other one wants to drop it down 4 volts, the result is 1 volt. I could send a 9 volt pulse this way and a 4 volt pulse, a negative 4 volt pulse this way, and when they meet, the 4 and the 9 subtract and you get 5 volts on the voltmeter. If I send a 9 volt pulse and a 9 volt pulse, when they come together and cross, it goes up to 18 volts. If I have a 9 volt pulse and a negative 9 volt pulse, when they cross, you get nothing. There are going to be places when they cross, while they cross, there are going to be places where one wave wants to go up and the other one wants to go down exactly the same amount. And because they travel at the same speed, they have the same frequency, same wavelength, same amplitude, they are always going to cancel. And what we're going to get are places where if I put a voltmeter, if this is my transmission line, which is really carrying the signal now, there are going to be places where if I put an RF voltmeter at that spot, it will read 0. Those are called nodes. As the two waves pass each other, there will be spots on this transmission line. You can locate them with a voltmeter, an RF voltmeter, here, where the voltage is 0. The peak-to-peak voltage is 0. In between, there will be places called antinodes, where the voltages always add. This wave coming through wants to go up. This one wants to go up the same amount. They go up twice as far. You get an antinode. And if we allowed this bugger to reflect off the end, the voltage at these antinodes would be exactly twice what it was before. So we get no voltage, bigger voltage. This is called a standing wave pattern. Standing wave does not mean that it's sitting still. That's not what it means. The pattern stays still. The pattern of interference stays still. That's what you mean by a standing wave. If the two are not the same amplitude, this is what's going to happen if we reflect off of, let me go back over to the computer. If we reflect off of a open or shorted line, here's the open circuit here on the right. Here's our source here. So we send the waves down, bounces off the end, and then we get this pattern where now here they are only drawing, in this photo here, what they're drawing is just the top part of the signal. If I go back to my whiteboard, if I just look at the size and wipe off that, that is what is being shown in that drawing. So we can see that there are places in either case where here's a node where the voltage drops to 0. Here's an antinode, here's a node, here's an antinode, here's a node, here's an antinode, and so forth. These can actually be determined with a voltmeter. And historically, this is how the wavelength of electromagnetic waves and radio waves was measured. They actually had a pair of lines like this. They're called lecture wires. And by moving a light bulb across the lines, they could find where it was maximum, minimum. You'll notice here that the distance from, if I can move this, the distance from one node to the next is a half of a wavelength. You can see down here, here's a half wavelength, and over here is a full wavelength, and over here is 1.5 wavelengths. The distance from one node to the next is a half wavelength. And by actually setting up a standing wave like this with an electromagnetic wave, a radio wave, a microwave, or something, you can measure the wavelength. This sort of thing, by the way, happens in a microwave oven. You have microwaves bouncing off the walls of the cabinet. There are places where the microwaves cancel. Those are the nodes, and the food won't cook at that spot. And then there are other places where they reinforce, and the food will overcook. So what do you do with the food? You rotate the food Yeah, I see it. You rotate the food so that it moves to the nodes and antinodes, and it doesn't burn in one spot and not burn in the other. The early microwave ovens had a stir in the top, which would stir the microwaves and move the antinodes around. But either way, it comes out to be the same thing. Now, what would happen if you terminated the line in its characteristic impedance so that nothing came back? Then what you would have would be just the one wave going out, and if you made a graph of it, you would get a straight line. The wave going back, you don't get the standing wave pattern, which means that if you put your voltmeter anywhere, it always reads the same value. You get a straight line, and that's called a flat system. You'll say you'll say the system is flat. It means it has no standing waves, which is a desirable condition most of the time. Most of the time. What happens if the two waves, if one of those is like this and the other one is like this, but they're the same wavelength and the same frequency? Well, then they can't completely cancel out. So what happens is if some of the wave is reflected. Now in this one, you can look at either the solid or the dotted, but you'll notice if you look at the solid one, which is current, it doesn't drop down to zero. It doesn't go all the way down to zero. It just dips a little bit. See, the less it dips, the flatter the line. If it didn't dip at all, you would get an absolutely straight line. One of the ways of specifying, I'll switch over here, or measuring the amount of mismatch, this is how it was done in the old days. So if we draw the standing wave, but only the upper half of it, so it looks something like this. All right. The voltage is high, low, high, low, high, low, high, low. If this is the maximum voltage, let me make this bigger so you can see it better. You've got to make things big. Make them big, Latta. So we got this, 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 not quite. This is V max, and this is V minimum. The deeper this dip, the larger the standing wave. If there was no dip, there would be no standing wave. So what we do is we say the voltage standing wave ratio, ratio means a division, is the maximum voltage divided by the minimum voltage. If you look at this, this voltage is roughly twice that. So if you go on the transmission line, I use open wire line because you can't rip coax open and get inside of it, but transmission line you can. You go out and you measure the voltage and find where it gets to the maximum, then you find where it gets to the minimum, you divide the two, that is the voltage standing wave ratio, or the standing wave ratio. If the maximum and the minimum are the same, it's 1 to 1. It means you have no standing waves. It means you have nothing being reflected back. If it is an open circuit or a closed circuit, the minimum voltage is going to be 0. And anything divided by 0 is infinite. Now that doesn't happen in real life, but it can get really, really, really high. So the standing wave ratio is a way of measuring how much energy is being reflected back from the load. Okay? Now, common misconception. You say, if the energy is reflected from the load, it's lost. No, it's not lost. It travels back here to your transmitter, and it bounces back, and it bounces back and forth. Meanwhile, the transmitter is trying to feed in more energy. What happens is the voltage builds up on the line. If the transmitter can get the energy into the line, and a lot of transmitters, you can imagine if the voltage here gets too big, that can damage your transmitter. So most modern radios have shutdown circuits. They sense the voltage is getting too big, it's going to blow those FETs. Nope, we're not going to do that. They cut down the power. So having a high standing wave ratio here at the transmitter end can cause problems. It'll reduce the power going in to save it. But the energy that's reflected back is not lost. It travels backwards, and then it comes back, and eventually it will make it into the load. So the voltage standing wave ratio is the difference between the maximum and minimum. Okay? So here you can see, this is what I just drew. This is about an SWR of 2 to 1. Now, I got to talk about, go back to the board. I talked about old wives' tales. And one of the old wives' tales is the SWR has to be 1 to 1 or it won't work. Rubbish. The SWR in my system is probably 9 to 1. The problem here, is when we go to measure things, there's true standing wave ratio and there's indicated standing wave ratio. This is what a standing wave ratio meter is going to read. It is, in most cases, not the actual standing wave ratio in the system. However, this is what we are concerned with. The physics of it is very complicated. But I can tell you this. Suppose you have a 50 ohm antenna, and you have my open wire line. This is just an example. 500 ohm line. One thing you can show is this. For a resistive load, that means an antenna that's tuned to resonance, the SWR, the true SWR, is the impedance of the line divided by the termination impedance. Okay? It's the impedance of the line divided by the termination impedance, so you flip it over. In this case, the actual SWR is equal to 10 to 1. 500 divided by 50 is 10 to 1. That might seem like it's terrible. However, on this end, this is connected to an antenna tuner, an impedance matching device, which can adjust it and turn it into the equivalent of 50 ohms. So that if this is an antenna tuner, and then your rig is hooked up here, this is your SWR meter, and then your rig is here, you're going to adjust your antenna tuner so that this thing reads 1 to 1, and your transmitter is perfectly happy. But the actual SWR is 10 to 1. What's even more remarkable is this, is if this is long enough, if this is half a wavelength, if you cut this to exactly a half a wavelength and you connect an SWR meter right here, it will show 1 to 1. If you hook your transmitter up, eliminate the antenna tuner, and hook your transmitter up exactly a half wavelength down the line from a 50 ohm load, it'll think it's a 1 to 1 SWR. And that's what you're concerned with. That's what you're concerned with. Now, if you try this with the opposite way, 50 ohm line and a 500 ohm resistor, okay, the SWR is still 10 to 1. This will be 500 ohms here, which won't work with your transmitter, so that's not good. But if you could match this, you could take, this could be coax. This could be some kind of a high impedance antenna. This is going to be bad. When you have the reflected waves, what happens is the line loses your precious transmitter energy. The voltages across the coax become higher than normal. It causes heating in the dielectric and heating in the metallic conductor. Now, in open wire lines, that's not a problem because the current's already pretty low and air is a perfect dielectric. But if you look at this chart here, I think this is probably where I want to probably kind of quit. I'll talk about matching networks and then we'll stop. Take a look at this. This is a chart that shows how much extra line loss you get because the true SWR is larger than 1 to 1 because those waves are coming back and the voltages are higher, the currents are higher, and so forth. What you'll see here, first of all, with open wire line, let me switch to this one. If I go to line loss, way down here is open wire line, right down here at the bottom. That one little sloper there is open wire line. And it's less than 0.4 of a decibel. If I blow this up, over the entire high frequency spectrum, 100 feet of open wire line doesn't lose more than 0.2 of a decibel. That's it. So with open wire line, if we now look at what happens, I'm going to switch. If the original line loss is 0.2 of a decibel, hell, when the SWR gets to 20 to 1, which is up here, whoops, hold on. Here's the 20 to 1 SWR line, or here's the 10 to 1 SWR line. The additional loss is barely 1 decibel. 1 decibel is the minimum change that an average person can even detect. It's insignificant. But if you look at, say, RG58 coax, which is very common, that's a smaller coax. Let me go to back to our line loss. Here's RG58 up here, right up there. And I'm going to go, I know it's hard to see there, but if I go up to about 30 megahertz, let me move this. If I move that up to there, the loss at 10 meters is about 2.5 or 3 decibels. Here's 3 decibels, which means half of your power is being lost in that little coax line on 10 meters if you have 100 feet. So let's just call it 3 decibels. That's close enough. Now, let's look at the additional line loss if you have a high SWR. So here's the loss would match of 2 decibels over here, or of 3 decibels. If you have an SWR of 5 or 7 or even 10, you have an additional loss of 3 or 4 decibels, which means in a case like that, you use 3/4 of your power is lost in that transmission line. If you operate that small coax at a high SWR like that, the coax is going to lose 3/4 of your power. What it comes down to in practical terms, is that, if I go back to my board, whoops, coax, keep the actual SWR below about 3 to 1. Now this is assuming that your transmitter can feed into this. The trouble is, if the SWR is high, I think most transmitters nowadays can adapt that. You can tell your automatic antenna tuner, it'll adapt it, and as long as it's below 3 to 1, you're okay. With open wire, anything is okay, but you must use a tuner because, first of all, the impedance of open wire line is high and you're going to have to adapt that. So let me finish with one thing, then I'll cut off here. A lot of people out there buy expensive antenna tuners. I use a PALSTAR, but for many, many years, you can use a tuner such as this. If you just have a coil and a capacitor, this is a variable capacitor. This can be a coil with an alligator clip on it, so you can just change the inductance while it's off, please, while it's off. This will match a remarkable number of situations, okay? This, of course, is what a lot of commercial tuners out there, and this one in B, you hook it up this way and see if it works. This is a variable capacitor, variable inductor. You can also hook it up the other way, switch the input and the output, or no, switch it the other way. Here we go. That's the wrong one. This one. A is just B flipped over. So you flip the input and the output around, and A is B. Okay? And if you take a look at F down here, you can also run the coil to ground and the capacitor floats, and D and C are the same thing, except the source and the load are switched. Okay? Source and load are switched. And if you look at E, E is A hooked up to B. So if you take the load from A and hook it up to the source of B, you get this, which is called a pi network. And if you take D and C and hook them up together, you get this, which is called a T network. But I'm willing to bet in a lot of cases, especially if you've got an end-fed wire, a lot of you folks are going to have an end-fed wire, you'll find that something like this, variable capacitor and a coil in series, might just do the trick.